So welcome to day 3, session 4.2b, a short introduction to data science and its application. So on day 2, you have learned about Expanse HPC system, how to interact with Expanse and other HPC systems in batch and interactive computing mode, how to manage data on file system, some concepts on parallel computing, high throughput computing, data management on Expanse. Today today we will learn about data science and applications. We will see what is data science workflows, uh, a scientific workflow tool to develop data science workflows, and data provenance. So do I need to, okay. And all these data science projects require proper data management. And Subhashish Dasgupta, our computational and data science researcher at SDSC, will explain managing mixed model data, give you an overview of Polystore, and building knowledge graphs on top of it. So at Workflows for Data Science Center at San Diego Supercomputer Center, our mission is to develop methodologies and tools to enable collaborative workflow-driven data science and create solution architectures on top of big data and advanced computing platforms such as Expanse. So the common theme is big data, computational science, data science, cyber infrastructure, and their applications. So the problems we are solving are the data science applications. So I've divided my first half of the session into 3 parts. Introduction to data science, where we will see what is data science. We will see some of the data science applications, and we will learn about data science workflows and Kepler scientific workflow tool, which helps you to build data science workflows. So what is data science? So different people have different perspectives. Some people think, generally bosses in industries, they think that their data science is some kind of money printer. Some thinks customers thinks that data science is some kind of magic. Software engineers generally think data science is a black box with some machine learning tools, some statistics, and they give answers. So in our view, data science involves infrastructure, software, statistics, data sources, and getting actionable information from the data. Let's go a little bit deeper into data science. So we have already heard about this definition that data science is to get insights from data and put it into action. This is what is data science generally defined. Let's see how we do a successful data science. So by applying a combination of exploratory analysis and modeling on variety of data sources, we get some insights. And this insights is some kind of data product, like visualization dashboards. It could be a web interface, it could be some APIs, and insights, like finding insight is not just one-time uh, static analysis problem. It is like once you have initial insight, you again feed into your models to improve them and then get better insights. So it's a dynamic problem. It's not just one-time development of models and getting insights. So one of the definitions we can say is data science is developing data products that facilitates an end goal through the use of data. So one of the examples classic example, Amazon.com, who recommends books or recommends products to users based on customer demographic, previous purchases, book review, and using all that data, which is historical as well as near uh, real time, to give feedback on what books users will like, customers will like. And this book recommendation is again fed back into the data to improve the model continuously. So one of the action is to find potential audience, like the same information can be used by Amazon.com to find potential audience for a new book. And in that way, so who is likely to like this book is an insight, but then marketing the book to right audience is action. So using the historical data plus real-time data to predict and provide insights and give actionable information to users is data science, uh, is an application of data science. Another application is weather forecast. So depending on the prediction of weather today and tomorrow, you decide what are you going to wear today, whether it will, if it is foggy or partly cloudy, you'll have a wind cheater, or if it's raining, you'll have umbrella. So, data science can be defined as systems and models that help us to understand data in order to gain insights and make predictions leading to action for impact. So data science is impact science because it helps. So like in book recommendation system and in weather forecast, it's helping customers to to recommend a book or some kind of like outfit that you want to try for that day. In the similar way, business leaders and business leaders or scientists can draw insights from raw data to create some impact on business or on science that they are performing. So this is kind of a flow or a workflow, like step by step, how you do data science. You get raw data, you prepare your raw data, then you build some APIs, which is like product in form of visual dashboards, web interfaces, programming interfaces, and you include them in some kind of platforms. It could be a web platform, it could be a robotics platform. And this preparation of data, you use algorithms to get insights, AI algorithms, and build models to feed into this products. So we can divide these steps into two parts, acquiring data and preparing data. We can define them under the data engineering umbrella, and then computational data science includes analysis, reporting, and then publishing the results, visualizing. And all these steps depending on the data, can require scaling. So it's a continuous iteration, integration of uh, these steps in a scalable form. So scalable data science process is you understand your problem or business, then understanding of the data, preparing data modeling, and then getting uh, for insights from your data, and then deploying the product. This is the cross-industry standard process for data mining. And then together with scalable data and compute systems and services and technology. So all these steps require scalable data and compute systems. So data science is bigger than the parts that we mentioned. So you get actionable items from your raw data, and you require certain sets of data science skills to get those actionable insights. It could it required some kind of Python programming, statistical analysis, machine learning, scalable big data analysis to scale your AI models, and data preparation steps. So we have seen mostly that data science requires mathematics expertise, technology hacking skills, and business and strategy acumen. And the intersection of that is data science. But if you zoom into it, you'll see more what are the individual expertise that we require. So it requires data engineering. When we are doing data science, it requires data engineering. Then you should know scientific methods, math, statistics, advanced computing, data visualization, domain expertise in the field that you are applying your data science. So these are uh, some of the expertise that you will require when you are doing data science projects. Uh, uh, so if you can go through them. So do actually data science exist? Because I mean these are like if you go into each individual expertise, um, they are like white subjects in itself. So do you think actually data science experts exist with all these skills? So the thing is, data science, as you have seen, this is like the collection of expertise that you need to carry out data science projects or endeavors. It is a configuration of various infrastructure, software, data collection, data verification, machine resource management, service infrastructure, monitoring, your tools and software applications, analysis tools, then the program management, feature extraction, then the ML code. We generally think ML code is everything in data science, but there are more parts to data science projects than machine learning itself. So the solution are complicated. We need heterogeneous systems and infrastructure, data management, machine learning, statistics, analytical methods, of course, scalable process management, dynamic coordination and resource optimization. Then we need interdisciplinary team. So data science is not an individual sport, it's a team sport. It's a V science. So data science requires data engineers, data analyst, method expert, scalability and operation expert, business managers, business analyst, scientist, visualization and dashboard developers, solution architect, storytellers, coordinators, and project management. So all these expertise are required when you want to carry out data science projects and develop data science applications. Let's go over basic steps in data science projects. So acquire. to acquire, import raw data sets into your analytical platform is one of the initial steps, first steps. Then you prepare the raw data, you explore, you visualize, you perform data cleaning, then you analyze the data, you create features on top of that, you do a model selection, you analyze the results, and then you present your findings. So these are like the top level steps when you are carrying out a data science project. And then once you have your findings, you use them to to do some actionable. So data collection from diverse sources in itself is a big challenge. It could be from relational database, non-relational database. Data could be in form of text files, CSV, live feeds from sensors, online platforms. Data ingestion into analytical platform. This is the next step where you want to get data to the platform where you are analyzing and exploring models, building models. So it could be Python and data can come from online resources and databases, sensors, file system. Then the next step is data preparation. You use statistics to explore your data, to visualize it, to just see different properties of data. You use statistics to do that. And data cleaning is very important because sometimes there are missing entries, there are garbage values in the data, nulls are there, and to clean the data, we need to remove those entries. We need to sometimes we impute the entries with average values, or we assign 0 or -1. That depends on your application. Another part of data science project is to visualize the data, and the visualization of data is very important when you are also presenting your insights to customers, and also before you are preparing model and selecting which model to apply. At both the time, data visualization is important. Then you apply some kind of, you apply analysis and modeling. You do supervised learning on top of it, unsupervised learning, semi-supervised learning. And once you from your machine learning model you get outcome, you then present the data in some form of visual dashboards, or you display that on web interface so that you can convey that to your customers or to the teams, other teams involved in the project. So summary is, if you see broadly, we have a few major steps like acquiring data, preparing data, analyzing the data, and then reporting the insights, and then getting um, actionable insights that you can apply in your business or in your scientific domain. So this is a general scenario when you are developing a data science projects. You have variety of teams involved. Uh, it could be data engineering team, then the data management team, uh, then there will be user interface team, AI and modeling team. And then the data comes from variety of sources, from people, from sensors, from bots, from some activity and transaction depending on the application that you're developing. And those data are stored in different systems, and then you need to bring that data to your analysis platform. And that analysis first is you explore which model to be, so you prepare the data and then you explore which model to be applied. And then once you decide on the model, then you scale it and deploy it on your compute resources. And the outcome of your analysis is a scientific discovery, or can be used in business domain. And this process is repeated, as we saw, to improve the model and to get better insights. So uh, today our big data science problems are are challenging because we have big data from coming from variety of sources, and then we have options of different computing platforms with diverse scales to apply to. So this enables dynamic data-driven applications, and all these applications that you see below are using big data. And then we have choices of selecting different computing platforms, which one is right, or how do we get from this data sources to insight is a challenge. And this challenge we have seen in different scientific domains like smart manufacturing, personalized precision medicine, then energy management, wildfire, precision education. So our research goal is to create a data science solution ecosystem that enables best practices. It should be data driven, scalable, dynamic. It should be able to use heterogeneous resources. It should be accountable and reproducible, so that there is an integrity in the insights and actions that you are presenting. So your science should be accountable and reproducible. Uh, it involves collaboration from multidisciplinary teams. So it's so this is yeah. So the point is, data science solution is not just providing actions and insights, but a system that is accountable, reproducible, scalable, and can use heterogeneous resources depending on your scale and application. This brings us to our next part, which is data science workflows. So what is, in this part, we will define what is data science workflows. We will describe three ways in which workflows can empower data science research. And then what are the positive impacts of data science workflows on society. So if you see, like we saw earlier, the steps to achieve a result or insight is like you configure some software, you acquire the data, and you move the data to some cluster or your analytical platform. Then you run experiments, and these experiments is like analysis and modeling, and this could be parallel experiment, or it could be a sequential experiment. Then you move the data, once you get the results or insights, you move data for post-processing. And then the results from post-processing is displayed either on the dashboards or some kind of data products. And then you could archive, or you can have a feedback loop to improve your models. And to run this experiments, you have choices of scripting using makefiles or workflow systems. So some of the examples of so we do workflow whenever we are doing some science. We generally use workflows, and or we are doing any real world problem. Any real world our actions can be also termed as workflows. So like when we are going out of city, so we book tickets, we pack bags, we drive to airport, we can check in person, or we can do it while driving, while other person is driving us, like when we are in Uber, and then we fly out of city. So these are like steps that you take to achieve some um, to get some results. So when you are doing a data science project, you have certain steps, and those steps, as we saw, can be divided into some discrete steps like acquiring data, then preparing data, analyzing data, and then analyzing the results that we get from the analysis steps. So, and some steps need to be done in sequential manner, but some steps you can do it in parallel. So, like checking online and driving to airport can be done sequentially, or if someone is driving you to airport, you can do it together, like in parallel. So this brings us to the topic of scientific workflows. So scientific workflows are set of computational steps that scientists use to generate some results or insights that can be used in some form of action to improve your business or your scientific applications. So scientific workflows combine multiple cyber infrastructure component in an automated process network. So you don't have to like do once. So it is not like individual steps uh, running on different infrastructure, but you can make it in an automated workflow, scientific workflow that you can run on heterogeneous computing environments. So computing today has many shapes and sizes. So we have big data from where the raw data generally in many applications are big data and comes from variety of resources. And then it is and then we run our models on different computing platforms and at a scale, and that enables the data-driven applications. And this requires and helps to have a software that can do a dynamic coordination and resource optimization, which is workflow systems. So scientific workflows are used in variety of scientific domains, and some of the examples that we have used scientific workflows to develop data science workflows are computer-aided drug discovery, smart cities, disaster and resilience response such as wildfire, then smart grid and energy management. We have used in personalized precision medicine, smart manufacturing industry projects. So, how we are supporting scientists. So you have when you are trying to come to a result or insight, you have some conceptual flow of steps, right? You acquire data from here, you do data preparation, then you do some analysis, you combine results. So there is a napkin drawing, or you have individual steps that you have developed some kind of like programs to do individual steps. Scientific workflow is when you turn your conceptual workflows into an executable workflows. So it can have like different steps where you see these are the actors which can perform different steps like acquiring data, then analyzing data, and then and producing results. So some of the advantages of using scientific workflow is you build once and you can run many times. One of the thing is like when you are exploring, you can build your pipeline, and then you can run it on different platforms as you scale your application or as the data volume increases. Scientific workflows also help you with the accountability of your science. So, once you have your process built into scientific workflow, you will the scientific workflows like Kepler, they save the data provenance associated with your data science workflows. So it can be which data source was used, what was the version of the data used, what were the processes or the steps that you took while drawing insights from raw data, who were the collaborators. So all this information in the background is saved by data provenance, which helps in accountability and then reproducibility. So data and process provenance generally saves inputs, outputs, intermediate results, then what were the steps, which step was linked with which step, the parameters used in each step, and then the version of the software and the data that you have used, which helps with the reproducibility with little effort. Once you have your process in form of scientific workflows, it is easier to document all the aspects of analysis. You can share your workflow pipeline with your team, reports. You can generate reports. You can have provenance of your of the analysis that you have done, and you can share that provenance with other team or publish it so it can be reproduced, and then it helps you with accountability as well. So saving and sharing helps in collaborating with different and interdisciplinary teams. So workflows help end-to-end scientific process from building a workflow with different steps, uh, because most of the actors are already built and you can drag and drop in the visual interface, and then you can build your workflow pipeline steps into your workflow. You can deploy and publish your scientific process with other team members. It helps you to run and execute workflows on different heterogeneous computing platforms, and it promotes learning because it's easier to generate reports, and then you can do provenance analysis. So if we summarize, it accelerates science by helping us to develop the workflows in a fast and accelerated manner. It helps to adapt to different heterogeneous environments. You can interconnect your workflows with other workflow system, uh, and also the if you build workflow once, you can reuse the entire workflow or part of the workflows in other workflows. Like if the data preparation steps are shared between two different applications, you can reuse those actors that you have built or part of workflow that you have built. And also once you develop the workflows, you can um, run the workflow behind the web interface, or some students or like whoever is starting in the project, it's easier for them to execute the workflows through the command line or graphical interface without having too much understanding of the individual steps. So let me just check what is the time. Okay. So there are infinite ways to create workflows, and you can create simple workflows, which is like sequential workflows, as you see on the screen. This reads a file from the input source, performs some sequence alignment, and then you display it on the using the display actors. Then there are workflows which use multiple components, like you see here. This collects data from web portal. It performs some R-based analysis. Then one step could be R-based, other step could be MATLAB based, and the third step is C based. So it can combine multiple different components, and then finally you get results. So in the same workflow, you can have steps that are based on different programming platforms or languages. Then here you see a workflow which is a flow cytometry workflow, and so it transforms the input data and display it on the web portal in the front end. And this is run in the back end of the web portal. It gets the data from the front end, transforms using R, and then user can give feedback from here if they want to go for a filtering step or not. If they don't want, they can skip and perform the flock analysis, which is a C-based program. So this is one of the workflow. Then here you see a compute and data intensive workflow, and it involves multiple steps, and you can see some steps are sequential, and then here FR hit, it's a parallel step that you can run on HPC cluster and in parallel, and then you can have two branches in your workflow. Other can use an assembly, can do assembly using Velvet or SOAP de novo, and then go to the steps like RPS blast, and which are again run in parallel. So that was the conceptual workflow, and this is the Kepler-based automated workflow that we built. You can integrate various cloud resources into your workflow as well. So then this is the Ember-based GPU molecular dynamic workflows. Here, different steps like minimization. So this is one of the workflows which combines both CPU processing and GPU processing. So minimization step uses CPU execution, and the heating step requires GPU execution. And you can, from your desktop or local machine, send the processing to expands CPU nodes or expands GPU nodes by just giving some parameters and configuration, like what is your identity file, what is the target host, and the number of jobs you want to run in parallel, and then some minimal parameters to run the MD workflow, like the molecular dynamic configurations. And then this will run in background without even having insights of what minimization is doing, how it is launching jobs on expanse. You are like, it is kind of creating an abstract layer between the computing platforms you are using and the user, and hiding all the complexity behind these actors. So benefits are, you can configure your MD parameters from the web interface or from the graphical user interface. You can scale this workflow at different levels, like at compound. Compound is the different execution you can run in parallel. So based on your compounds, you can scale this process on uh, the entire pipeline for different compounds. And then you can use multiple computing platforms like GPU cluster and CPU cluster, and you can also run different steps on different clusters altogether. Like, one could be on your local machine, one could be on one of your lab clusters, and the third step could be on expanse, depending on the resources. And this, because you have your process in a form of data science workflows, it collects provenance in the background, and then it can be reproduced, or it could help you in publishing. And also you can reuse different actors into different scenarios. So let's say if you do not want to have heating step in one of your workflows, you can just connect configuration module, minimization, and equilibration, and then just skip the heating step. So you can reuse your components. And then you can share this pipeline with your teammates. You can generate execution reports. Another example is in which we use data science workflows is in hydrological data analysis of hydrological data analysis. So here we have we do so there is a US, across US data, where you define your area that you want to simulate using your shape actor. Then you do subset of the entire continental US data and run your analysis on power flow, and then you can do further analysis of water balancing and drought analysis based on your power flow simulation for that particular area. And we used a Kepler scientific workflow to develop that, and it helps you to run your workflow on different computing resources, and you can have your workflow cater to different users, like educators and domain science users, which are like end users just want to visualize the results. They can visualize the results. Then modelers have want to run different power flow simulation models. So they can use the entire pipeline, while the the analyzers want to use the post-processing steps of the output of the power flow simulations. So you can plug and reuse different components and cater to different users using that. Another system that we developed for one of the data science application is for Quantum Foundry, where we are we are collecting material science data from different scientists, and then we are curating and managing their data and providing an interface in which they can enter their process, how they develop different material science. So most of the time material science processes fail. I mean, they are developing quantum materials, which is like a next generation materials. And most of the time this processes fail, but there are insights which you can use when you are developing your next quantum material, or which other users can use, like why the steps failed, and depending on your historical data and current steps that you are using, you can provide an insight to users that what should be your next step. So this is the platform that we are developing for Quantum Foundry material scientists, called Quantum Data Hub, where they can search and query the previous data processes. They can visualize, and based on that analysis, they can apply the insights action into developing the new quantum materials. So you amplify the value of Foundry data through data science using this platform. So this is the notebook process that material scientists people use to create their workflows. And we are providing them with an interface which you can use by dragging and dropping on the web interface and create your procedures. Like you use gallium chunks and selenium as a starting material, you grind, and all these steps can be documented on digitally on Quantum Data Hub, and then you store the metadata of each step and see if the entire process was success or failure, and give that insights to other users when they are developing the next procedure. So from lab notebooks to the digital interface that can provide actionable insights to material scientists. This is one of the very good application of data science. So this is the architecture. So we have the complete solution for them, from the web interface to the backend, which uses object store to store their data associated with material scientists, quantum materials, and which could be data like snapshots or data coming from characterization of the quantum materials, and then the metadata associated with all the data that you are storing on samples, as well as the process that built that sample, is stored in the in database, which helps you to give and then this Jupyter Hub, using Jupyter Hub, we analyze the data and then provide insights to user for next generation of next quantum materials. Another example of data science workflows is, so I'll quickly go over smart manufacturing. So this is like from edge devices, you acquire the new data, you use AI models where you are acquiring the data, preparing the data, training the AI models, and then a model is evaluated. If you do not have the performance that you desire, then you again retrain your model. It's like dynamic process rather than static. And once your model is you approve your model, then you deposit it to a repository, which can be used at in the edge, like on the small scale manufacturing companies, where it takes the edge data from edge sensors and then give insights to the workers on the ground. So this is the conceptual workflow, and then this is the workflow that is developed in the Kepler scientific workflow system. This step ingests raw data, then you do data processing, and then there is dynamic decision support system, which helps you to see if the model is good enough for use at the edge. Another another application is TempRedict, where we are using big data system for scalable exploration and monitoring of personalized multimodal data for prediction of COVID-19. So even before onset of systems, monitoring your physiological data indicators through wearable devices, we provide prediction whether there are chances of you having COVID in next few days is there or not. And this is the system where scientists can explore and develop their data science models. And once they have finalized the data science models, it is automatic. This provides a platform where they can deploy it automatically in the production environment. And this system uses Kubernetes cluster to do that. Another example is of workflows that we use for wildfire, and here you have big data that comes from real-time sensors, weather forecasts, landscape, fire parameters, and then you apply Wi-Fi models, and you then monitor and visualize the insights that you get from your AI models, and then predict the real-time spread of wildfires and actionable insights. Another project that we are developing right now is for prescribed fires, where you pre-plan the fires so that you reduce the fuel in an area and reduce the wildfire. So I think it is 10:45 already. So do I have, yeah, I'll quickly go over some of the Kepler scientific workflow system that we have seen right now, so many examples. So Kepler is a scientific workflow system that uses Ptolemy as in the background, and to create scientific workflows, and it's an open source system built on Ptolemy framework. You can think Kepler as a toolbox with many tools. So there are actors that you can use for accessing database, for doing I/O operations. There are already pre-built actors there that you can customize for your application. Then there are compute actors that helps you to do data parallel patterns, execute your jobs on HPC clusters. Then you can it has tools that helps you for data provenance and fault tolerance of your data science workflows. So this is the UI of the Kepler, where you see workflow canvas here. And then There are components under which you find actors and directors. And actors are the units that perform some function, and director is overall controlling unit which executes the workflow. So you can see here the teal colored square is actors, and then the director helps you to execute the workflow. It defines which actor will trigger when, and it's like a movie. Actor performs their role, and director tells you which actor will trigger when, or will conduct their role when. And then there are parameters that can be customized by users. So actors are the processing components. They can be linked by connections, and they have attributes. They have input and output ports, which are used to link one actor to another actor. And we have some simple actors which performs one function. We have composite actor which have more complex sub workflows inside them. You can see under B there is a interconnected sub workflow. So we have a lot of actors in place in Kepler, which are command line wrapper tool, execution, local execution, which performs SSH, SCP, FTP. So all these actors help you to move your data from your local machine to HPC cluster, to expanse. Then we have web service clients where you can use SOAP and REST APIs. We have cloud computing actors to spawn your VMs, instantiate and manage them. Then we have job actors, which submits job to HPC and CPU using Slurm, PBS, and different schedulers. So you don't have to worry about like submitting jobs to Expanse and managing them. These actors take care of that. We have Spark integration. We have integration with, we can integrate it with external workflow engines like KNIME. And one of the powerful actor is multiple execution actor. So using this actor, you can develop one workflow and then execute it in local manner, or you can do remote job execution, or you can do on heterogeneous platforms. And you select your execution choice with a drop-down menu. We have Kepler suite that is for bioinformatics, and it has bioactors which help you to wrap your BLAST, BLAT, and different kind of bioinformatics application inside data science workflows. So basically, big picture is to support scientists from conceptual workflows to executable workflows. So yeah, so with that, we will go to the next section. As we already mentioned that data science applications require proper use of data management and then connection between different kinds of data sets to get interesting discoveries. And Subhashish will give you insights how we do data management in some of our projects. Thank you, everyone. And if you have any questions, I'm open to.
Shweta, do you have a break now, or we can continue the session?
We can just see if we have any questions, and we can take those questions quickly, or we can do it at the end of the.
Yeah, folks, feel free to unmute. We don't have anything in the chat, but if anybody has questions, just unmute yourself.
Maybe I can just show quickly a Burn Pro 3D application that we have. So this is Burn Pro 3D platform for proactive fire management. It helps with the prescribed burns. It helps fire chiefs and land managers, burn bosses, to do a pre-planned treatment of an area so that you can minimize the wildfire chances there or mitigate it. So they can use this platform, they can decide on the, so these are different burn units, and let's see one of the burn units, and they can analyze the, so from the data, you can analyze uh, different runs or weather conditions, like which are favorable for doing the prescribed fire. So you see here, we display what is the unsafe. So this is 46% unsafe, and here you see only if you follow this weather condition, it is 15% unsafe. That is very less, so you can conduct your prescribed fire in this area. So it gives you insight of what should be your weather speed, wind direction, and if you have, this is this surface moisture, then these are the windows to conduct the safe prescribed fire. So this is a analysis dashboard which is powered by AI in the background, and to get the actionable insights for fire chiefs and burn bosses to conduct prescribed fire. So this is a very powerful example of data science application that we are developing. So I'll stop sharing, and if you have any questions, we can take, or Subhashish can take over.
Shweta, was that example referencing the current Yosemite fires?
Yes.
Oh. California,
Yeah.
really
this,
difficult.
yeah. So this is like prescribing fires for areas so that the wildfire can be mitigated. If you use the fuels, if you use up the fuels by pre-planning the fires, then the uncontrollable wildfire can be avoided.
So do you have a break or no break?
I think we can continue, Subhashish.
Okay. So yes, hi everyone. This talk is more about how you will use your data, how will, as Shweta mentioned, how you will manage, monitor, and use the data for your system. And so the name of the talk is managing mixed model data using a polystore. So what is polystore? I'm coming at the later part of this talk, but mixed model data is something what we experience every day. And the talk is I'm Subhashish Dasgupta. I'm a assistant scientist here, and I'm also working on the data platform these days. My PhD background is on secure data system. Uh, so coming back to the mixed model data, we all experience with the different kind of data in our day-to-day. Like we use data from different devices like oceanography scientists get data from the sensor, ocean sensor. And so a material scientist get data from the instrument. And also in modern days, there's a new term called digital medicine, where people use the different kind of body parameters and other kind of data like blood report and pathological data, and then using them, they try to predict try to predict the various possibility of various diseases. Like during the COVID, we are also engaged with a project where we are collecting data from a ring called Aura. Shweta already mentioned that project. That is called Temporary project. In that project, we are collecting the biovariable data from the Aura, and we are also having a survey. Then we are trying to predict that if the subject or the patient has chance to COVID or not. Depending on that, we are recommending them for a COVID test, and we run that thing for a longer period of time. We every day we send alert to the UCSF hospitals, and that's really helpful. In other way, in the material science, we are also trying to achieving a material repository where we scientists or researcher or engineers can record their experiments, and on the other way they can use those values to understand or design the next set of experiments. The main advantage of doing such kind of thing is that you can reduce the cost of your wet lab, and you can move faster. So as a result, the data become a centerpiece of every science, and different devices are producing the data in different form of way, and we are storing those data in a different format, like in the file format, or we are in some cases we are dumping in the database. Now, while different devices and different methodology, different algorithm are producing the different data, they have distinctive model depending on their processing nature. For example, if you have a geospatial data, that will have a different format, where you have a relational data, or in some cases when first you may have a text data, or you may have a time series data. So we have data, and we use those data for our experiments. So that's why we are calling them the mixed model data, because in real life you can experience a different model of data in your experiment. So if the data is very small, then you don't have any problem. But problem starts with the when data is large, when you are handling a large set of data. In a typical scenario, if you put your data in a database, or that may be a SQL, NoSQL, or file, so our pipeline is like this. We have analysis, which typically we represent in a Jupyter notebook, because Jupyter notebooks are very popular. You may have other programming interface here, but for every case, we connect that with a database connector, and we send the queries to the database. Now, depending on the database, you have different choices, but the main factor for this database is you are retrieving data smartly. Means the objective is you can retrieve data using this connector very quickly from a database, and you can use in your application. That application may be feature extraction for the machine learning, or populating a map, or generating the cohort for a training data set, such kind of stuff. So what is your intention is your pipeline should read the data appropriately and quickly. So this is the whole scenario. Means we need to retrieve the data faster, and well, we have a huge database. If we do something, so here is an example of or a comparison. In the first box here, if you see, this query is about searching a text in a database. So we have a huge collection of Chinese newspaper. So we are searching a text in the database. In the first case, in the first case, we don't have any index scan there. So the database designer didn't perform a very efficient job, so he avoided the index. So if you run a data without the index, then your retrieval will be slow, which is a known thing. But if you don't know about those kind of stuff, your life will be miserable, because all of your experiments, all of your process will be very slow. So it is important to understand what kind of database we are using and how we can optimize that. But before that, we have another problem. Another problem is that if you, as we mentioned, that we may have time series data, we may have text data, we may have other network data. The bottom line is you couldn't feed them into one database or one model, because every model has their own capability, and depending on their own capability, models are very much tuned with their nature. Suppose you are using a network data, then the network database will allow you to traverse from one node to another node through its path. But if you are doing a similar kind of query in the relational database, it's sometimes it's very expensive, and it's very costly. Similarly, if you are doing text search, like if you are doing inverted index or any kind of text search, any kind of string search from a large text, and if you put that data in a relational database, then it's not the proper way to do that, because relational databases are not good for large corpus of text. On the other hand, if you have aggregate, or if you have a statistical query, then you should have the relational database. But if you have time series operation, then you need to look for a time series database. So the bottom line is, no one size fits all. So what we will do? So where do I find these databases? So this is an information. If I want to model my application, I need to choose suitable database. So where should I go and find the database? Yes, there is a website called gbgb.io. If you go to that that website, and if you search for, you can see on the left panel there are different criteria you can choose, and you can see the you can see the feature of the database and the purpose of the database. So this is one way you can go and smartly pick a database for your application. But you need to choose the database depending on your application, how you will design your data pipeline, how you will design your flow. Depending on that, you can choose your proper database from here. So as we already talked about the different models, so it's already, you already understand that there are model specific database, like for relational or aggregate, or those kind of queries solved by one class of database, where the graph and other queries are solved by a different class of database. So we have different model specific databases available in the market. For example, of a few model specific database, like for relational database is particularly the where the most common database, like a PostgreSQL or Oracle MySQL Server SQLite, they have a full length of relational algebra. you can do all kind of set operation using this relational algebra, and you can build your query. Next is the graph database, where you can put your network data. Sometimes you need to do network search. You need to understand the network behavior. In different science, we need to study the network analytics. So for that purpose, you need to go for a graph database. Similarly, if you want to do text search and other kind of search, the Solar Elasticsearch, those are the very much search specific database. So you can put your data in the search DB, and your text search will be faster. If your data is not relational and it has more nesting, like a JSON object or a XML object, you need to have a semi-structured database where you can run semi-structured query. Like you have nesting in your data. You want to do nesting queries, so you need to go for MongoDB, or there's another DB called Asterisk DB. It's a UC product. It's from UC Irvine, so you can use that database. They allow you to almost similar kind of SQL style query on the semi-structured database. Postgres also have a semi-structured plugin, but that is not efficient like the Asterisk DB or MongoDB. Postgres also has a search plugin, but again, that is not efficient like Solr. So if you have huge data, and if you want to do search, it's always better to choose a Solr or Elasticsearch over Postgres. Similarly, if you have time series data, then you need to do time related queries, like creation of time bucket, creation of time window, overlapping window, tumbling windows, all those kind of time related operations. Postgres or any other database is not as efficient like this time series databases. So if you are using a time series database, then you need to go for time series data like timescale DB, influx DB, and there are a few more in the recent days. Similarly, if you have spatial query, like you are querying on the map, you are trying to get the data for a particular geo boundary, then you need to have a spatial DB. So we have a few models described here, and you can see we have all different kind of databases we are using. Also, we have a few examples, like for key value storage, where you are querying on the triple, or where you are storing your keys. So you have a key value storage, the Redis, RockDB. Those are the efficient key value storage. Moreover, there are a few things like Dask or like pandas. They are very popular these days. They basically create a data frame and allow you to do a class of queries on the data. So we all are familiar with pandas. Those are in-memory solution. You will load all the data in the data frame, and you will run a few queries. You can run a few queries on that. You can do processing. Those are very popular and very efficient, but doesn't provide any more sophistication like a traditional database. But they have downsides and upsides as well. So we can compare. But here is our data scenario. So if you need to manage the database, you need to manage your data efficiently for your experiment. So designing part is very important. You need to choose your proper databases. So before designing the whole thing, you should consult a database expert to manage your data properly. So that's my advice. so let's say a small comparison between three popular databases, because we will work on this database today mainly. So as we mentioned, the Postgres is the relational database. It has a good SQL query facility. It can do cube and group by queries, but it is not as efficient for the search. Although they have a generalized inverted index or generalized inverse search tree, but those are not so efficient. They cannot do the network queries, so you cannot run a class of network analytics like centrality computation, PageRank, and other stuff on the Postgres. Similarly, if you choose Neo4j, Neo4j is not relational. It's mainly for the network, so they don't have any relational structure. Instead of SQL, they have a language called Cypher, which will allow you to define your network query. They are not they don't do the cube and group operations like in the Postgres SQL. You can do a cube and group by operation to create a group and see the group statistics. You cannot do that in the Neo4j. In Postgres, you can also use some additional statistical libraries, but in Neo4j I have not seen those kind of libraries available. But their graph analytical library is very sophisticated, so you can try that if you can model your data like a network. Similarly, so naturally the network queries and the network analytics are very fast. The Solr is basically an inverted index which allow you to do a text search, but it's not for the network queries or the network analysis like centrality and PageRank. So here our three candidates which we'll discuss today, so that their capabilities and the shortcomings. Now, coming back to the Polystore system here, since 2016-17, people are coming up with a system which can help out in this situation, like which can actually provide a model specific efficiency on the data. So we call it Polystore system. The design goal for the Polystore system, that Polystore should support location transparency. Location transparency means where it's actually storing the data is not transparent to the user. That means users need not to bother about the storage. So whenever you will store the data in the Polystore system will store it in the appropriate storage, and it will rate the data if required. It will index the data as needed. Then the semantic completeness. Semantic completeness is I want to say that the user will not lose any kind of capabilities provided by the storage system. That means, suppose in your Polystore system you have a relational storage, suppose Postgres, and Postgres has a cube by facility or group by facility, which is inherently provided by the Postgres solution. The system will keep that capabilities. That means system will not cut any capabilities, or it will not lose any capabilities when it will integrate the data. So you will have a union set of all the capabilities provided by the underlying storage. Then the thing is object version consistency. So that means when Polystore is spreading the data across the storage, it should maintain a consistency of the version. That means if you have a network data, if you have a network model data, which is basically built from a relational table, relational data, if you have an update on your relational data, system will automatically update the network data or the other data. So that means the data version will be consistent across the storage. Then it will have a capability-based optimization. Capability-based optimization means suppose two of the underlying database has same capability, like Postgres has a search capability and Solr has a search capability. If so capability optimization means if you are searching something in the Polystore system, if it's better served by the Solr, then system will perform the search from the Solr system. Now the architectural variation of the Polystore. So we have seen people are coming up with three different architectural variation of the Polystore. First one is loosely coupled, second is tightly coupled, and hybrid. The loosely coupled Polystore is basically you will add the store or the cross-model mediator, and you will have a dedicated provider which will serve the each store, but there will no centralized controller for the loosely coupled. In fact, in the tightly coupled, your underlying storage will be governed by a centralized controller. The challenges for a loosely coupled solution is across the storage, the view materialization or cross-model index is very tough here, because every model will have their own index, and how you will join across the index is still a problem. But for tightly coupled, you don't have those problems, but each time you are putting the data, you need to transform the queries on its own model. So there are upside and downsides for loosely coupled and tightly coupled. So now people are trying to come up with something called hybrid model, where you have all the facilities defined, or where you will have all the efficiencies, and the architecture will be optimized as per depending on your application. So if you in real world, if we have 7-8 Polystores available, we have the big dog. That's the first Polystore from MIT. They are basically a loosely coupled model. Then you have INRIA's Cloud MDSQL. You have UCSD and INRIA developing Estocada. Then we are working on Awesome, and we are serving a few projects using the Awesome. So we are coming up with the Awesome. And then we have Polystore Plus from Stanford University. Microsoft, a few commercial organizations, Microsoft is coming up with Polybase, and HP Lab is it's called OOX. There may be other Polystores, but these are the main Polystore system I can see in the market. Now, Awesome as a Polystore. Why when we start building the Awesome, we started it for the social scientists. Now we are working with material science, health science, and other projects. But initially, when we started, it started like we have a different model of data. Like you can see in the left side of this presentation, we have the data variety. We have social network data from Reddit, Twitter, YouTube. We have newspaper data. We collect different newspaper every day here in US and across the world, China's newspaper. So we have a big newspaper collection. Then we have contract and legal documents. Then we have clinical trial data. We have emails. We have other financial documents. We have chat and other kind of data, SAP data. So and on the other hand, we have a few associated data like dictionaries. Dictionaries are for interpreting and the data from various domains. We have a few packages. We have some human intervention in the data. So that was our data scenario initially. And then when we are storing the data, we are storing like this. We are storing the YouTube data in the asterisk DB because that is the semi-structured data, and Tweet and Reddit, YouTube, they have the same semi-structured model because they have nesting in the data. Then the relational data we are storing in Solr for text search, and for other statistical calculation we are storing in a Postgres. For contract and grants, we are also storing those in the Solr database for searching. For clinical trial data, we are storing that in the Postgres. For other world data, we are storing in the various storages. So we have quite a mixed data scenario for this project, and we choose different database to store those data so that our query can be efficient. And social science, so questionnaires were like this: list all the account mentioned in the Elizabeth Warren, and also talking about American US movement. Find 100 top influential users. Those are co-spiking and talking about the racial term in this network. Find top K queries from the newspaper and discuss about the Elizabeth Warren in network. Another top K queries covered in the network but could not cover in the newspaper. So if you look at the queries, you can see that for the for these two queries, they have text search, and then also they have tweet search. Means you need to do a top K queries in the newspaper, and then you need to find out the Elizabeth Warren, which is a network query. So if you look at the query number 3 or query number 2, you can see they have two parts. One part is coming from the relational database, another part is coming from the network. So you need to join that data, and you can produce the result. So this is a typical mixed model scenario where your query is starting from one storage, and it's basically sending a portion of the query to the another storage, and then you need to join back the result and produce the output. So this is the scenario where we started building a polystore, because such kind of system was required here. So what we did, we basically created a this is a mature architecture. After a few years, we came up with this architecture where we have a few storage like relational, graph, and asterisk DB, and text search database, and we have a stack of libraries on top of that. So this is so this architecture is actually tuned for serving the queries through through different storage, joining the data, properly and allow user to run a SQL query or text search query efficiently without knowing where it's going. So we covered a few requirement of a polystore architecture. So this is the polystore architecture we patented later on, and this is this is a intellectual property of us which we are using in different project. Now we perform different projects using this polystore. As we mentioned, we performed we are working on a material science project, and we are working on a digital medicine project. We are working on a we are working on a security project. So one of the case study I want to mention here, where the scenario was like this. We worked with US Navy research and Navy research department to understand their priorities from the public data. They assigned us to determine where Navy is working well compared to the other countries, and where it's lagging, and what they are not doing by analyzing the public data. So public data means so the problem was like this: discover all the technological gap in some domain, and who can bridge those gaps. The data set was patent data, newspaper data, and all the publicly available data, and SBIR data set, where which company is working on which project in US. And so the solution approach we presented them, that is basically creating a knowledge graph, which is a graph, which is on the graph database, and searching a term and then joining the knowledge graph with that term to get the additional term, because this knowledge graph is basically built on the ontology, where you can have semantic connectivity of a particular technological fields with the other fields on that domain. So, and then you can search a text and go to the knowledge graph first, and you will get all the related terms, and then you will try to find out all the patents and all the publications that from the Google patent and Google Scholar database, and then try to find out a timeline, which is a temporal query, to discover the gap. So we did this thing with following kind of data. Like we got the patent data. Patent data is basically text data with some network information. So we analyze we ingest the patent data. We extract the text portion, put that text in the polystore, and we create a network who is working on that patent, and the organization who invented that, or in later on they sell the patent to somebody else. Those kind of information from the patent, and we put them in a graph database, those network information. So you have a innovation network in the graph. Then we have scientific publication. We did the similar thing with the scientific publications, and we extracted the information and stored it into the polystore. Then we have 170 or something like that online newspapers. It covers most of the news, and we also process them and stored in the polystore. Similarly, we have SBIR STTR American Seed Fund. That means these seed funds are like if you are expert in a particular domain, or if you want to do something which is very new, then they will fund you. So so this database contains which company works on which domain, and and what is their expertise, what is their contact address, those kind of stuff. We also got the US spending data. US spending data is available, and there you will find some military spending in which sector. So now, if you look at this database, we have patents that and publication. That means we know in which technology who is working on what, which country is working on what. You can go up to the country level, and you can also see that from the patent ownership, which company owns which patent, which technology, which in a timeline wise, which company is improving on this technology, which country is ahead of time from the other companies. Similarly, from the scientific publication, you will get the similar kind of innovation knowledge. From US spending and other newspaper, you can understand that what people are US is spending in which technology and where US newspaper is talking about. So if you combine all those things, these are the public data where all are publicly available data, and now you want to analyze those data. To analyze those data, we put all this data in the Polystore, and Polystore shred those data for the in different model and store it into the appropriate database. Now for answering their queries, we divided the whole process into three part. First part is the search, where it's search is like if we are talking about search, then the most common thing is the Google search, where you will put a text and you will get the related web page or website where that text belongs to, or which is related to that text. Our search was a little bit different. We'll show this demo at the end of the session, where if you search a thing, search a term, it will basically give you the different 360-degree view of that term, which technology is related to that term. It will go to the ontology and find the network link, which technology is related to that term, which country is working on that technology, what is the statistical timeline of that technology, and a basic version of the network. Then we can ask the system, find out the gaps. So they mentioned they mentioned that a list of countries, those we marked at the different status, but apart from that, gap analysis specifically tells you that which country is working on that technology and what is their timeline. You can find the different gap structural position. Like, so for example, suppose you are searching for UAV, and system will go and find that there is a dense region for a dense connection with UAV, and then FPGA and the chip development. So that's that triangle system will automatically discover, and it will find out the statistics on the other documents, and it will try to rank the gaps, and it will show you that this technology fusion, or in this triangle, the US is what is the status of the US. Now, last part of the system was, if you have the opportunity, if you want to improve that, find out the organization those are working on that, or find out the collaboration opportunity in the US. So that basically, it's this query is basically answering from the SBI database, where companies are registered with their capabilities, and you can find that if those your gap capabilities, or where you are lagging, who is working on that. So you can basically from a search you will basically getting ground level information where you should go. So that was the purpose of the whole system. Now how we designed it, how we designed it with our logic, and we spread the data into the different database. Now coming to the demo. So I will show how this system is positioned in our server. We have, as we mentioned, that we have 3 different databases. Just a moment. Yeah. So this is the dashboard of the application, and we have a newspaper database and patent database is running at the relational table. You can see we have new in this table. You can see this is a Postgres database. We designed it with the newspaper, and you can see we have the news ID, then title and all those things. So when we put the newspaper here, we basically traded the newspaper into this newspaper table, where you have a news field, where you have the collection date and other field and published date, author, keywords, etc. But this is a Postgres database. So as we mentioned, the capability of Postgres database is running groups and other queries, but text search is not very efficient here. So for the search, we used another database called Solar. This is the Solar database running here underlying. So Solar, in the Solar, we have just the text field and the news ID. So this ID will basically join back the news in the Postgres database. So if you search something here, it will be very fast. I can search a term, it will be 1,000 times faster than Solar. So our search, any search is coming from the application, it will be very fast here. Then the other information like the patent and other stuff, we have a relational part, and we have the search part indexed here, and the network part, the ontology and other stuff we stored here, which we called network database. Here you can run those network query, and here you can basically store your network data on the basis of the relationship. So you can see we have different nodes, and different nodes are connected with different paths. So basically from here you can understand that we analyzed the problem, and we created a data plan, and we stored different data in the different storage. And at the top of that, we created a layer, which is our awesome layer, which basically connect all those things, join and query on this data, and give you the answer. So here we have the basic dashboard. This dashboard UI is not very fancy. It's a part of a student project. So now the first term, we have never related things, so we should start. I'm searching the first term, the UAV. See, it's so when I search here, you have UAV. The first thing happened that it went to the database, search database, the Solar database, and find all the newspaper related to the UAV. Before going to the search, it basically first it also collects the related terms from the ontology, which is in the graph database. So this portion of the data is coming from the graph database, where it says that UAV is related with drone, sense and avoid system, ground system, and UAV. So according to the available data, the system is believing that UAV is connected with this kind of this set of data set. If I change this term, like let's say radar, it will go to the ontology, and just a moment, it's possibly bringing a yeah. So if I search the radar, you can see it brought a whole lot of term like radar equipment, radar signature, radar mapping, and other stuff. This is basically we are serving these things from the ontology. So the first portion of the query, it basically it's going to the network database and finding those terms on its network connectivity. Then it's using all those terms, it will go to a search database and search the related documents. You can see it's already searched the related document, and it says that in the newspaper you have this orange portion of the data, where in the patent you have green portion of data. So radar related patents are green data, and the radar related news are this orange data, and you can see a thin publication line. So radar related publications are in this position. This is according to the available data. And if you go here, we have a foreign ally and we have a foreign adversary. This is based on the Navy requirement. So they selected a few countries according to their strategy and planning. So you can see this in this case, for the position of the foreign ally like this, they have 14,272 patents, but this adversary group has 6,919 patent, and also you can see that United States has a quite a position like 23,000 patent. Among them, US Navy has 5,787 patents, and other government has 470 patents. Now, if you go to the timeline, you can see whatever we collected from the ontology, the related ontology. This is the timeline of the innovation. It's coming from 1903 to 2019. So you can see that these are the patents filed on that year. Like so, if you just hover over this line, so you can see the you can understand the innovation timeline, and you can see that where people are working and where people are not working these days. So you have an idea of what other what is going on in this field. And if you are going to the network part, then this will give you the exactly the ontological view, where you can see these terms and how those terms are connected. You can see the radar equipment is connected with radar reflectors, and that is connected with the radar clutter. So you have an idea about how these systems are actually how this network is actually in the ontology. Now, if I can do the UAV search again, or we can use any other terminology. So let's do the UAV, it's faster. You can see that in UAV, you have not that much stuff. Here these statistics of for the different different groups like United States, foreign ally, and other stuff, the innovation statistics. And here the timeline of the UAV. Here, if you can see the drone system, they're really spiking up after 2012. So they have more innovation. Now second step is we need to find the gap analysis. So we will select all this field, and we'll say ask the system to show the gap analysis. So here, remember when I was talking about the gap, I was talking about the gap triangle. So system automatically analyze the network, and it will give you a version of gap. So here, if you look at this term, so that means UAV tracking and computer vision. In this triangle, you have this innovation where you can see the US has 686 patents, where China has 759 patents. So China is basically have more patent than US. And if you look at the timeline after 2015, China really published a lots of patent than US or any other country. Similarly, you can see that that Portugal, Denmark, they have also one patent in this area. Similarly, we found another gap in UAV, AI, and computer vision. Here also, after 2017, China start publishing more patents than ever, and it's beating US in technology innovation. In the area of deep learning, computer vision, and UAV, it's the situation is also China is leading here. So we have another gap, that UAV situation awareness and computer vision, UAV trajectory optimization, and computer vision. So these are the top 6 gaps that system analyzed data and found that gap. There may be many more gaps. That depends on the triangle computation. When you are asking for the gap, system basically going to the network, it's calculating the triangle and creating the aggregate statistics from the relational database. So when this gap analysis is actually happening, it's first going to the network to get the triangles, and then it's going to the relational database to get the aggregate statistics from the triangle. Now the last portion, when we are so if we want to bridge gaps on, say, US UAV tracking and computer vision, or maybe the UAV situation awareness or computer vision, we have a button called opportunity. You will click that opportunity button, and sorry. You will click that opportunity button, and it will show you the different organization from the SBI database where these companies are working. Excuse me. So this is basically, here you are analyzing the data, and then you are mapping it with the real organization from the SBI analysis, and you have those address, and you can contact with them to discuss about the innovation plan, or you can start working with them on various plans. So the whole system is basically it's gathering the public data, then analyzing the public data, and mapping it to the real organization. And we have, as we mentioned, we have different data set, and we created those data set. We ingested those data set. We shared those data in the different storage and created the query pipeline. So this is a typical example of a polystore system where you can you can map your application to the ground, map your application to for the different model of the data. So then going back to my presentation. So this means this example shows that even if you have a complex data situation and you have a complex analysis pipeline, you need to choose those data storage, and you need to build the pipeline properly in order to analyze your data. You people have your own data pipeline. You have your own analysis pipeline. But when you are choosing your data set, when you are choosing your storage, you need to keep in mind that the capability of the database really matters. A full fledged available polystore is not available these days, but it will be available soon. But now when you are using your data pipeline, you should be careful about the processing capabilities and other capabilities. So this is all. Any question about this presentation? I can take those questions now, or you can send me email at su-gupta@ucsd.com. I will answer those.